Okay, so uh, for today's class, we are going to focus on some feature engineering and transformation at large scale. And then we have a series of labs that we want to go over. It's an interesting quote by Andrew Ng. Coming up with features is difficult, time-consuming, and require expert knowledge. Applied machine learning often requires careful engineering of the feature and data. It goes back to the same thing you have seen so far. The most important part of any project is that, data part. Then you have the rest of the pipeline. The modeling part is not that important. But for us today, we're going to talk about squeezing the most out of your data, the art of feature engineering, and the whole process of it, and how feature engineering done in practice. Okay. So when we say squeezing the most out of your data, it basically means that to make your data useful before you're passing it for the training, be sure that to represent the data in a certain forms that the model can basically learn from, increase the predictive quality, and reducing the dimension of the data. So you always want to have the best quality, but also as much as possible the lowest dimension, because that's reduces the overall cost. Feature engineering, like everything else in ML that you have seen, is going to be a loop, basically. It's going to be an iteration. So you combine set of feature, you tune some objective, you basically make some new features, launch it, you learn something, go back, and you do the same. So it's pretty rare for you to, at first iteration, to have all the features that you think is important. You always come up with some features, test it, deploy it, you find some errors, come back, build some new features, and continue with that iteration. Okay. Now, we also talked about this, that in basically typical ML, you need to be sure that during the training, whatever processing you do, you apply the same processing at the inference time. It should not be, there shouldn't be any discrepancies among those. Okay. Now, there are a couple of key points here. That first, feature engineering is basically difficult and time-consuming, but important. You need to squeeze the most out of your data, concentrating predictive information in fewer features. It's better than having too many features also. Now, let's do a couple of things. So we're going to talk about certain types of pre-processing today. It's going to be from textual data, categorical data, numerical data, and then we're going to map that to a large scale. How you can basically use at a large scale, maybe using something like Apache or TFX and or TFT or PyTorch transform. Now, when we talk about the pre-processing, we start with data cleansing, which you all know. This cleansing idea is like, okay, anything bad from your data, you remove it, or maybe you're dealing with the NAND. Then you have feature tuning. Anyone? What's feature tuning?
Like suppose our values are like decimal, then we have to scale it up.
Yeah, something like a scaling, normalization, and stuff like that. That's a feature tuning. Representation transformation. What do you think of that?
Merge into embeddings.
Yeah, embedding is basically one of those. Feature extraction. That's just basically when you do kind of like something like a feature selection to pick up the best, most important features. And then feature construction, which is when you build new set of features from whatever features you deem important. Now, in general, your goal is that whatever you raw data, you have to map it in some sort of like a numerical representation for your model, because models are normally basically require that numerical vector. Now, if these days we don't do one-hot coding much, but it's just an example. For example, if you have a street name, it's something as a string. So instead of basically passing it in that way, you, as part of your feature engineering, you need to have some sort of representation for it, like a numerical. In this scenario, we're basically doing one-hot encoding. Maybe the number of neighborhood or the streets in this example is really limited, so it's easy to do one-hot encoding. If you deal with categorical, basically vocabularies, what you also want to do is that, again, TensorFlow, it's the example that I put, but in PyTorch is also the same. You could basically have some sort of function that, given some vocabularies, it basically does that one-hot encoding for you. Or you can also read, like you have a file on your machine that contains list of all these categories, and you can load that and convert that to a one-hot encoding. The benefit of something like TFT or PyTorch transform is that they are fast in process. So they basically, it's better than working with Python, plain Python. So when it comes to empirical knowledge over your data, if you're dealing with text, you do a stemming, lemmatization, TF-IDF, n-gram, embedding, anything basically that you could give you some basically deeper contextual knowledge about your data, about your textual data. It's useful over there. When you work with images, clipping, resizing, cropping, blurring, filtering, and so on, those are basically help you to either change a little about your image or learn certain features, extract certain features about the image, like edges, colors, and stuff like that. In general, the goal for you is that to be sure that you have a data preprocessing that can transfer the raw data into some clean and readable and easily like data set. You need to basically do certain feature engineering, that the goal is that to route the data into feature vectors, integer values, basically to be sure to convert it to floating points, normalize the numerical range, a string and category calls to some sort of like numerical vectors, and so on. Now, let's do a couple of, so every time I hit one, it goes two. Okay, let's just start here. So, when we are talking about the feature engineering techniques for numerical range, could be a scaling, normalization, a standardization. You could do something like a grouping, like a bucketizing or bag of word. But the important part that you need to remember is that all of this, like when you do a scaling, normalization, and standardization, in nature, they kind of do the same thing. What they do, they just enforce the range of your data to become kind of like a more narrow, but they are not changing anything about the nature and how your data looks, the shape of the data. For example, let's go here. First thing we come back to this. If we do normalization, which what it does, it enforces the data to go to range 0 and 1 from whatever range it is actually. On the left, the original data that you have, on the right is the normalized version. So what you will see is that despite the fact you change the data, like the original range was between 0 to 400, now you're at 0 to 1, the shape of the data, the peaks and the downs, it's actually hasn't changed. It's just squeezes the value. So it's not changing anything specific about the nature of your data. The same thing with a standardization or a z-score, which basically brings the data range to from -3 standard deviation to 3 standard deviation. That also does the same thing. It just changes the range, but the shape of the data remains the same. Now, let's go back here, past one. And then if you're dealing also constantly like a scaling, you could just do also scaling, for example, for images, which you do image minus 127 divided by 127. Oh, there are different ways that you can do that. But in general, when you deal with a scaling, normalization, and standardization, the goal is that these types of processing, they do help your model to converge faster. Neural networks basically have a harder time if the range of values are basically wide. So, and it also basically helps you to not have NAN or NAN during the training. So when you see something like that, one of the reasons could be that your ranges are pretty wide. Okay. Now, on the other end, you can also do something like bucketization or binning basically. And here the idea is that, let's say you have years in your data, and you have some knowledge that, well, the year itself, year 1960 versus 1961, doesn't have any different, right? So instead of you have the years basically to be just integer, you create these bins or buckets. This is less than 1960, 1960 to 1980, and so on. Because you have, and this cannot be random, you know, technically you need to either have some domain knowledge or you do some study on it. One way to do a study like this is using something like FACEIT or ClassIt again, which we saw in the previous class. So it has a page. If you go on ClassIt, basically, you can select different features, and you can basically try to see the relationship of the features with respect to each other, and try to see that if you can bin, and if you bin on one feature, what impact will have on the other feature. So if you want to do a study, like you're not sure about how should I bucketize, you can use a tool like this. It's kind of like a visual tool for you to do that. On the other end, there are other techniques also, like you can do something like PCA, TSNE, and UMA to help reduce the dimension of the data, which again is recommended as much as you can always reduce the dimension of the data. Let's do a quiz test. PCA. Who can tell us what's PCA?
Finding the axis that contains most of.
That's correct. What type of dimensional reduction is this? Linear, nonlinear? Linear, right? So the idea of PCA again, is correct, is to whatever is your original data, instead of having it in that higher linear subspace, you bring it into a lower linear basically subspace by finding this new dimensions that are perpendicular to each other, right? What's wrong with PCA? What's the main problem with PCA?
Important features can be lost.
Important features can be lost. Great point. No. PCA, similar to bucketization, it keeps the shape of the data the same. If you do PCA and visualize it, it has the same curve as if you have the original data. Right. Hard to interpret, that's correct. It's like its interpretation is for PCA is really hard.
It's complicated when we have more number of features.
Complicated when you have one number of features. Could be correct. What else?
Spatial distance can be like smallish when compared with PSA in that.
So what he's referring to is that the local neighborhood versus global neighborhood of the thing. So in PCA, the local neighborhood is not preserved. The global neighborhood is preserved. That's why the shape of the data in general remains the same.
Assumes a linear relationship between features.
That's a big assumption, correct? So what else? There's one other one that's kind of like interesting. It's about how PCA treats basically different dimensions among this. Like if your PCA has 3 new axes, right? There's something wrong with PCA about how it gives importance to each one of this. So when you build PCA, the first idea is to find first principal component, correct? What does first principal component means for the data? The most variance, right? If you find this, what's the second principal component? Right? But this has all the freedom. As soon as you find this, where this one can sit, right? So it doesn't have much freedom. Then where this one can sit, perpendicular to both. So what happens in PCA is that as you go through the dimensions, adding new principal components, the first principal component has the highest variance, most amount of data information preserved. As you go through the rest, they don't carry much information. So it doesn't treat them fairly. You know, if you're lucky, you are the early principal component, you get enough information, otherwise, no. Now, TSNE. You can tell us what's TSNE. You always need to do dimensional reduction, so let's like a quiz. Let's
convert the data point to the higher dimensions, probability distributions, and then reduce they can match with the lower dimensions using TDL diagram.
So TSNE, T-distributed stochastic neighborhood embedding. The idea is that PCA is great, but what it does, it basically does not preserve the local neighborhood. What does a local neighborhood mean? If you have these points, right, local neighborhood means that in the original dimension, these two are neighbors, right? And like, I don't know, maybe just so random. Let's assume that these two have 80 feet distance from each other, right, as a neighbor. If you go to PCA, it doesn't guarantee that it will keep that distance. Maybe in the new dimension, these two become neighbor, and that's not the neighbor. The idea of TSNE is that how could we go from higher dimension to a lower dimension, lower new dimension, where if points are close to each other as a neighbor in the original dimension, in that lower dimension, they remain like the probability of being neighbors, 2 points, is going to be the same within the lower dimension compared to the original dimension. By doing so, you preserve this local neighborhood concept, and basically you have a better, like a transformation. Now, why we're talking about this? Because when you will work with the higher dimensional data, like especially this is like we work with embedding and stuff like that. If you want to see that, okay, did my embedding learn anything? Can I visualize my embedding? You need a way to bring from that higher dimension matrix into at least a 3D, like a 3D or 2D, and then visualize it. So there are some tools out there. One of them is called TensorFlow Embedding Projector. So let's see if we can. So this is it's by Google also, I think. Assume so, yeah, TensorFlow. So what you see is a pre-trained embedding. This is word2vec 10K. So you can basically select different one. You can also load your own embedding. If you have created certain embedding for your product, then you can load it. And because your embedding is in a higher dimension, technically here you see is 200 dimension. So you need to bring it into a lower dimension and in order to understand that if the meaning of the words are preserved. So here, basically, the option you have right now is on PCA. So if you go, basically the words closer to each other become neighbor. But I recommend you to try out the PCA versus TSNE. And you see that how PCA basically breaks that neighborhood concept, but TSNE does a better job. But overall, in general, for you, it's also important to understand, not just for visualization, which is great, but also sometimes for if your data is in a higher dimension, the cost of your pipeline or data processing is always higher when the more data that you have. Okay. All right. So I highly recommend you just play around with that TensorFlow projector. All right. So now the next thing we're going to talk about is called feature crosses or feature basically generation, or like probably that's the other name we have heard. Which the idea is that, well, how could we combine a bunch of features to build a new set of features that have a maybe better signal or basically learning information for us. This process could be simply you multiply a bunch of features together, you combine day of the week and hour into hour of the week. That becomes cross. And Normally feature cross comes, either you have some domain knowledge, you're like, there's a paper already published, especially if you are, for example, in healthcare, you can just cross features because it doesn't make sense, the meaning, especially if you want to publish something, or if you want to build a product, or a doctor wants to trust your product, you can just build feature that they don't have any meaning, right? So if you do feature crosses, it needs to come from some source, some other paper published it, and some basic knowledge around it. But if you are working with different domains, that doesn't matter how you build the feature, as long as it gives you the final outcome. There are so many mathematical ways that you can build lots of features, instead of doing the manual, you can just simply build like a multinomial set of features that helps you with the output. Although you need to be careful when you build features in that way using mathematical operations, that is also highly possible that you do some overfitting. So you need to also account for that. Then encoding features, here in this scenario is like if you do binary classification, you need to encode the features in 2 classes. And then when you have the same problem, now let's say you have this. So the problem here that you have is that this learning curve, every time I hit left, it first goes forward, the keyword, and then, all right. So here you see it was easy to separate. Here it won't be easy to separate because it's nonlinearity. So how could you introduce that some sort of like a nonlinearity? You can either do that by making your model nonlinear, or you can basically transform your data to account for that nonlinearity, right? So if you have these 2 classes, these points on the inner circle is class 0, outer circle is class 1. And it's called this x1 and x2. So one way of learning this is to focusing on building a model that has nonlinearities, to learn that, to separate, to build this decision boundary that they can separate those 2 from each other. Another way is that by encoding your data, that goes to a higher dimension where these 2 become linear. Right? So if you go basically to x1 2, x2 2, now for all those points, this is the new data set, same data set, basically. And all you need is one linear line to separate those from each other. Right, so even the data in that exists in a high dimension or in a nonlinear, you could basically convert it to a linear dimension to help. And that happens by some sort of like a feature engineer or feature processor. Now, so pre-processing data at a scale. I swear, the forward is always first backward, and then it need to escape Python. Anyway, so when you want to build data pre-processing, data pipeline, the reality is that Python is not a really good, basically platform or good language for them. These days is becoming better and better. Like lots of people are using it, but you're dealing with the data that comes from, it's like a large amount of data, customer data. You need a really fast processing. Probably Python is not going to give you that performance that you're hoping for. So that's where you need to go to do something like Apache or Java or something that basically is at a lower level fast. Again, Python is changing. I think, if I'm not wrong, last 2 weeks ago, 3 weeks ago, there was an announcement about the new Python that's is running at a different level. I'm not sure about the news exactly, but this apparently is going to make it much faster. You're probably going to hear about it soon. But so that's the first thing to keep in mind. If you're processing large amount of data, maybe think of outside of Python for your data pre-processing, not for your entire pipeline, but for the part that you need to be faster. Now, we also talked about this in the previous class, like we had that lab for the TFX, which data comes, you do some sort of like a example. The example generator is just simply means to load the data, load example. So for your data pipeline, you need a pipeline, something like that, especially the yellow bar. You need something that gets the data from somewhere, loads the data. You build some sort of like a statistic generator that's from the training data. You build some statistics from that. You build some sort of like a schema. Then for any new data that comes, you validate that data with the statistics and the schema that you have from the training data. And then you also have some sort of like a transform. And transform block, it simply is whatever pre-processing code you have that basically process the code, process the data if it was validated. So that means as part of a data pipeline, if the data comes through and it's not validated, it has a wrong schema, it has a wrong statistic, don't pre-process it. You can just somehow count it or create a log around it and reject it. Okay. And again, you don't need to adhere 100% to all of this. You can write your own decisions and just kind of like add it to your submission that we decided to do this for this reason. Okay. So, yeah, okay. And we also talk about inconsistency across in features, basically feature engineering, pre-processing granularity, pre-processing training data set, and optimizing the instance level transformation. Let's just start with the pre-processing at the scale of so many data. So you and your product, probably you just download this small batch of data, which we say that that's what happens in academy, right? So it's kind of like data is fixed, you just try to improve your model. In the real world, you deal with the petabyte or gigabytes, depending on where you work, of the data. So you need to be able to process a large amount of data at scale. At scale means that you know, if you have a customer that's online and that means right now they want an answer, they cannot wait a second or 2 seconds for every page that you are trying to process. You should be much faster than that. But if you are doing a batch basically processing, that means the customer upload the document, they don't want it right away, they can wait. And then depending on how much they can wait and what's the process, what's the definition of your product, you can collect some amount of data, and when your batch is full, then you process that data to save some time and some money. But all of that means that you need to have a consistent transformation between training and serving. We talked about this before also. The training serving is queue is when you build something using the training data, as soon as you deploy it, it will break. At the moment you deploy. Break doesn't mean that the pipeline breaks. It means that the result is basically off the chart. That's the training serving skew. And that's normally happens because you have your training and serving code paths are different. So at some point, the code that you are using for serving and inference, that pre-processing part is diverged from the training data for pre-processing. And again, the one way that we talked about this before also was to maybe combine the data pre-processing part into your model itself instead of having them to be separate. So data goes to the model and pre-processing happens over there. The benefit of that is that you can save your model PyTorch or TensorFlow as kind of like a light version, and you can basically serve it on as JS, as on your mobile, on your basic server or website. And it basically helps you to eliminate the risk of that training serving skew that you could have. But there are some challenges. There's some challenges with that process also. So, okay. Now, when you do transformation, you technically have two types of transformation. You either do instance level or you do full path transformation. Instance level transformation refers to any time that you process one data point at a time. The customer data comes through, you do certain processes on it in order to pass it through. That's instance level. On the other hand, when you do full pass is when you need information from the entire, like the statistics from the entire training data in order to pre-process a data that comes from your customer and passing it to your model. So instance level, something like clipping, multiplying, if you multiply values by something, expanding features or feature crosses, basically, that happens at instance level. You only need one data point. Full pass, if you do any of those bucketization, scaling, normalization, because that you need the statistics from the either a batch or training data, entire training data. That becomes a full pass transformation. And they all have their own pros and cons. Okay, so if you do basically full pass, you need to run it once, correct? But the concept could be transformation, basically like producing the transformation at your serving. The other process that compute on the entire data set, and then also has a slower iteration because you need to run it across all the training data that you have. But you can eliminate that to some extent by running it within your model. That means, again, bring your neural network. This is your neural network, and as early part of the neural network, you have the data pipeline. The benefit of that is, well, it's easier iteration, the transformation is guaranteed, but the cons of it is that it's more expensive. Why? Because when you go to the model, it takes basically more amount of, I don't know, depending on how you're doing it, on GPU or basically, and it causes the pipeline, the model itself to be slower, because now you cannot, maybe previously you had your data pipeline to be kind of like parallel processing or something, but right now everything needs to happen together, so it becomes slower, and can also get the transformation skew per batch. That's also possible because it happens across a batch. So it's kind of like it's your decision that if you wanted to do it outside of your model or you want to do it inside. This doesn't. You want to do inside of your model or you outside of the model or inside of the model. I'm going to use mouse moving forward. Now, on the other end, you can also do transformation per batch with something like, for example, batch normalization. You all done machine learning. What's the benefit of batch normalization? Anybody? What's the meaning of batch normalization? Okay. So if you have some sort of like a batch, right? And it goes to your neural network. Why do we normalize that before we pass it? To say that it. Weights. You need to like have weights which are. Okay. Right. So basically, you ensure that this data has always same distribution every time the data comes. So always has the same range. So what happens if you have layer one? So batch data goes to layer one of your neural network, gives you an output. That layer one output goes to layer two, and so on. Right. What do you think is the impact if you don't normalize over this data that goes across layers?
When we think about the activation function, it doesn't normalize. If they, let's mention it goes to too far right, and there will be a small, so it doesn't change.
So vanishing. So vanishing gradient is basically when the whatever you predicted, it wasn't that important. The gradient becomes smaller and smaller with them. So if you dealing with the data that goes through layers, one of the challenges that you could have is that this layer, weights of this layer depends of the output of this layer, correct? So if this layer always could generate any range of the output, so the output range could be from 1 million plus to 1 million negative. Then there are lots of fluctuation in the weights of this, depending on what comes out of that, correct? So instead of doing that, we enforce the output of this layer also to always be within a certain range, right? To normalize it. That's what you see in transformer. You see at every layer, you have that layer normalization because you want to enforce the values basically. It's kind of like a fix. This works on, there's a concept called Lipschitzness. I know the name is crazy. But the idea of Lipschitzness is that if you do batch normalization, the impact that it has is when a data point changes, right? So if a model basically, if a model is Lipschitz or similar concept called beta smooth, the impact of such a model is that for a small change in the input, the outcome is not going to drastically change. It's controlled. Or in the small change in the basically weights, the gradients are not going to drastically change. You basically, if you can force your model to be Lipschitz, it will have a predictable behavior depending on the input. You have probably seen models that as soon as you tweak something, the output drastically changes. Those are the models that the internal behavior is not Lipschitz. So a small change in the input or weights can have the drastic output. Anyway, so that's the whole idea. So you need to do some sort of like a batch transfer, batch normalization also, and well, it's just talking about the impacts that it has, but it helps you with the predictive performance. That's what we were talking about. It also helps you with optimization for on your GPU or TPU if you want to gain some efficiency. Now, we don't need the key points. Let's go to LLMs now. Now, pre-processing for LLMs is a little different because you directly just work with textual data. We're not talking about VLMs, so it's in this case just LLMs. So the first part of your work is always to ensure that you can convert the data into a textual format that you can use it for the training. How many of you have worked with the PDF data? Right. How many of you know the challenges in PDF data in text extraction? Every time I do an interview, that's one of the interview questions I put on any engineers that we're hiring. Because we do lots of PDF data, and I said that okay, like tell me about how you basically convert this one PDF into a text format. Right? It's pretty challenging, despite the fact that you are thinking that well, there are so many libraries out there. So if you have just one PDF text, easy to convert. Bring a PDF like something like an IKEA that has images, bolts, numbers, text, and then try the best PDF converter in the market and say that convert it. You see how the results. Why that's important? When you work with the LLMs, and especially if your data comes from PDF, you need to first convert it to some sort of like a textual format, right? So you need to also be sure that that textual format is accurate. The order of text is preserved, and so otherwise you broke the meaning of the document. The other thing is that you need to be sure that you get rid of the boiler points like a header, footer, something that's not important for the training. Filter out short or really long, maybe documents or text. Come up with some sort of like a normalization format, and probably for most of at least the fine tuning, often we use JSON-L format as the for every prompt response pair, which we're going to talk about. This is the idea of the JSON-L format. So if you're doing the fine tuning, build something like that. And again, these are varying depending on which model you are fine tuning also. So like we have different formats, but the idea will become there's a prompt and there's a response basically, and you build this data set of these prompts and responses to later to feed to your model. If you're dealing with the long text, so you need to do some sort of like chunking. When you deal with chunking, there's like a default idea of like a chunking by length and adding some overlapping window over it. I highly recommend you if only do that if there is no semantic or structural meaning in your document. If you have a document that has structure, and think about the structure means that you're reading a document and it has bullet 5, this is large header, and then 5.1, something. There are lots of text and you have 5.2 and something in. So when you deal with a document like this, if you want to chunk it, you need to do document aware or chunk or context aware chunking to ensure that you know this text comes from here and this belongs to here, even if they are not part of the same chunk. Because later, if you're doing some sort of retrieval, then that can give you that additional knowledge that's missing. Yes.
Suppose if we have a novel, then there's this whole context of it.
This one?
Context of it.
What was the last part for what?
Knowledge,
Oh,
text.
so yes, it should work. So textbooks basically they have chapters. Textbooks they don't. They have chapters. They don't have sub chapters. You know, so it would be basically chapter, and you just need to know which chapter this text belongs to. But if you're reading something like a journal article, like a medical journal, or like any paper that published, then if you just simply pick a part of the text and later you want to retrieve it, if you think about so many times in journal, not medical journals, same text repeats at top of the paper and also at the part of the conclusion, and sometimes within even the body of the paper. Right? So and just with a small change in wording. So if you're trying to retrieve certain part, you could get the abstract, you could get the conclusion, or you could get the chapter that technically has the entire paragraph. But if you, as part of your like a context aware basically chunking, you know that this paragraph that I embedded belongs to abstract, this belongs to the, I don't know, methods, and this belongs to conclusion. That could help you with the way that you want to retrieve.
I'm talking about. Like, suppose we have a book, like first page mentions the person, the last page of the book also mentions that person.
Yeah, I mean, I see where you're going with that, but that's kind of more like you see the way that you say it sounds like building a graph over the entities that you are seeing. So this is what we're talking about, is about how to chunk documents. What you are saying is that how to build some sort of like a knowledge around what document that we are parsing, if it's a book or not. And maybe later I can, if I want the data for anywhere there was a mention of the name Ramin, I could basically extract all of this from the document, right? Maybe something like that. Not necessarily that you need a graph for that, but that sounds more like a graph concept. Okay, so it's just an example of if you work with something like a PDF loader, basically helps you with just extract certain PDF, chunk it based on some size, and define some overlapping window for like a 50 words overlapping, and then store those. You could also do manual, there are other libraries if you don't use something like LangChain, like NLTK has it, Hugging Face Transformer has it, there's all like PyMo PDF has it. There's all, Duckling is one of the really good ones. I highly recommend you to work with that if you work with PDF. Pretty good. Those are obviously help you with things like this. And then at the end, when you want to build a data pipeline, or basically before building a data pipeline, you need to remember that there are a sequence of steps that you need to go through in order to pass the data to your LLMs. And then that could be also that understanding that if you want to do pre-processing for your training, or this is a real-time pre-processing for user input. And technically, they need to do this similar task, one as an online, one as a batch. So a typical LLM pipeline for data processing is like a data source, pre-processing, some sort of like a prompt inference, post-processing. And post-processing includes both guardrailing and basically alignment of the result that your model has. And that, if you work with LangChain also, it's just a similar idea, loaders, splitters, vector restore LLMs, just for you as an example. If you work with Hugging Face, it has some high-level pipeline API. It has different versions to say, so pretty good. But you could simply get the pipeline from the transformers and say that I want to do a text generation. This is the model that they want to use, and ask it generator to ask a question. It will generate it for you, and you define how many tokens that you want. How many of you have worked recently with Hugging Face Playground? 1, 2. There's stuff, you know. Okay, if you want to figure out which model you want to use and you don't want to spend money on it, go to Hugging Face Playground. You can simply select any model for free and test some data with it. Okay, it's already deployed, so you don't need to run a GPU, you don't need to deploy anything, it's already deployed. You just select the model that you want, pass the data that you want, get the result, and it has all the models basically. No, that's wrong. It has most of the models that Hugging Face has, because it's kind of like those are being sponsored by some other companies. The GPU is coming from somewhere else. But try that for your product. All right. So this is just an example summary. Let's say you are trying to build a support for daily tickets. That means that daily ticket comes to your company data, and you want to basically read those tickets based on that to take certain actions. So what you need as your part of your pipeline is that get the HTML data, if it says HTML for it, it's just an example. Normalize it, basically chunk it into meaningful chunks, maybe here 2,000 tokens. Pass that to an LLM and say that summarize this ticket for me, and then combine those chunks into one full summary, and then either restore it, deploy it, create a ticket based on that, and so on. But you just need to think of the process that you will go through. You could also do some sort of like an orchestration for something like that, working with Kubeflow or Airflow, or LangChain, basically, or LangFuse, something like that.
Let's suppose we will have a gatekeeper. In that case, we will not get any good data from our LLM. In that case, how do we do the post-processing?
What do you mean by gatekeeper here?
Gatekeeper means that, let's suppose I have something which is like good summary or bad summary, and I'm not getting the bad summary out to the end user. For that, I have gatekeeper.
Okay.
In that case, how will I do the post-processing step?
So you are saying that what I give to user is already filtered, right?
Yeah.
Your gatekeeper does the filter. So when you do, what does your gatekeeper do?
It just decides this is a good.
How does it decide?
I mean, there will be a metric for that, and
So that's called alignment, right? So you want to be sure that whatever the model produces is aligning with the expectation of the user. But if you are saying that my gatekeeper also checks for toxicity, checks for bias, and stuff like that in the data, that means you guard it. So post processing has a couple of meaning. I think we have a slides on it, but could be guardrails could be simply like doing an alignment, or it could be like a verification of the model output. Like you ask my model to return a valid JSON. Is this a valid JSON or not? So it could be as simple as that. Or you ask the model to, if it produce a result, always cite where did you get the answer? Is there any citation in the answer or not? Should I accept it or not? That gatekeeper could be multiple basically pieces that they all run, and if all of those passes, then you pass the data to the customer. Otherwise, you do a retry maybe.
It's the part of the post processing.
That's good. So now data quality. Validating, why we need to validate our data. And again, as I said at the beginning of the class, even if you don't have if the LLM that you are using, you need to do some sort of validation. So you need to have some good data for that task. But ensure that, your data basically accounts for your input, fine tuning, and the output are correct. Correct means that they are not basically hallucinated, or basically are not wrong from the perspective of nature. You're following the proper format that you're expecting, and they're reliable. Now, and I think that's basically most of what we were talking about. So cleanness and consistency, be sure that there's no missing values. The format is as you expected. Filtering for quality. If your data that has duplicate values, or you can do something like a hashing among text. You have a high basically similarity, just get rid of those. Human evaluation, it's highly important, especially when it comes to these types of things. You do some sort of like a human in the loop. You build these pairs of result, pass it to your model, get the answer, get those pairs to like labelers or raters, and to see that which answer human chooses, and later you use that for updating your reward model. It's also possible, and other students, they also did that. They use LLM as a judge. That means you pass the result of one LLM to another one and says that then you have a different prompt for it and says that if it's a good or bad basic answer. That works also, but just keep in mind the cost of, for every call you basically make 2 calls, and normally for the second model, which is the judge, you need a better model to be able to judge the other one. So that's something to keep in mind. You could have some programmatic rules. You could have simply a schema validation. So these are like the ways for you to verify if the output of your LLM is good or bad. Now, feedback loop and continuous monitoring. So this also comes back to what we were talking at the beginning of the class for the logging. So you want to be sure that whatever you monitor, you deploy, you monitor for it. That monitoring could be your output that you are generating. It could be the input that comes to your model. You could get simply feedback from user as a thumbs up, thumbs down. You could do some sort of like a inference, like a user ask a question and they repeat it again, and they repeat it again, and every time basically they don't like the answer that you're providing. That could be a negative sign. So it's either like a direct feedback or it's kind of like an inference. But you want to, if you can pass that to the model for update. If you are dealing with a schema validation in LLMs, like Pydantic is one of the easiest one for you to do that. You just need to build some sort of like a base model, and then whenever your model produces an output, you validate it against that to ensure that it gives you the valid, basically expected output. So we will have at some point one of our speakers, a friend of mine, Ben will come here. I think take a look at this report, BAML, boundary It's kind of like a made-up language model for LLMs. Instead of you trying to force the LLMs to produce JSON, you basically use BAML to force the LLM to kind of like have a consistent output. It's pretty easy to work with, but we will also have again lab on that when by this paper. But that's something else to look into. Data validation for fine tuning, but just be sure that if you're doing fine tuning, your database is strictly clean. And remember, having a smaller data is better than having lots of noisy data.
We cannot use Pydantic for data validation coming from LLMs, right? How do we do that?
So, why? Yes, you can. So, basically, what we are saying is that every time I call to LLM, basically, I say that I call to LLM, and let's say I'm getting a JSON as an answer. So, certain LLMs, especially, basically, they can give you a JSON as an input. And as part of your prompt, you requested the LLM to create this JSON with certain keys.
I see.
And keys has defined data types. So you build some Pydantic for you, some sort of base class for it, and you always compare it to this to ensure that it's valid from a schema perspective.
All right.
Basically, in LangChain, we use with struct output, you're saying we can validate with Pydantic.
That's correct. So, I mean, LangChain is, these are all examples. BAML is the library, LangChain is one, or you can just simply do Pydantic depending on what you're using. So, we're on time. The next thing is going to be tokenization, which lots of you need to remember. Every other semester students had these issues that not understanding the cost for your API calls. And then they lost all the credit that they had before even they start. Remember that models, especially the LLMs you work with, they basically working with tokens. Tokens doesn't necessarily mean words. You know, it's just depending on the type of tokenization, but it's kind of like a subword unit. This could be, you know, depending on tokenization that you use, either byte per encoding, sentence piece. It's all like a different ways of breaking a word, like elusiveness. You don't probably learn it all as one word. You break it into subunits, and you learn those subunits that are shared across different words. So why do you want to understand something like that? Is because you normally all the LLMs, especially these days, the cost is basically there's a rate per token. You know, so it's like a that's a way easy way for you to miss and miscalculate the cost that you will have. So just keep in mind that you know a token is almost 4 characters, and that means 4 characters basically means almost less than a word basically in English. So 0.75 words. In different languages, the tokenizations are different. For example, Como Estas is technically 10 characters, but 5 tokens based on different tokenization. It's really important to remember different models that you have different tokenization. Okay, different models have different tokenization. Some models, they come with the tokenization already if you work with Hugging Face, for example. And if a model has a tokenization itself, just use the same tokenization. Don't try to change that one. Then the other thing is that if you're dealing with the fixed vocabularies like maybe 50,000 tokens, what will happen here is that it will try to break the benefit of something like that is that if you do something like a byte per tokenization and stuff like that, if you can easily deal with unknown words by breaking down those into subwords. But why these are all matters? Because your context length matters, and then your cost of your calls, and also if you're dealing with emojis on your data. Okay, so the way that or image, if there's an image as part of your embedding, the text that you're sending to your LLM call, to your API, you need to always remember that the way that the machine sees an image is not just an image, it's actually the number of tokens are pretty high. So you can just simply send one image and have a cost of maybe dealing with 10 documents. So just these are things to keep in mind. There's an easy way for you to do something like that. It's called tick token. You can go to that, just import it, install it on your machine, or just go simply to the playground it has. I think OpenAI has also a really nice playground for tokenization. And just put your, let's say you're dealing with a, as part of your product, you have large amount of prompt that goes to your LLM, then the data goes. So one way for you is that to understand the cost is that because your prompt is always fixed, see how many tickets is within your prompt. That already tells you that you always will have this fixed cost for just processing the prompt. And based on that, you can also understand how many more new tokens the model can generate given my prompt is this length, plus the data that will go into the model. So it's really important, try to understand your tokens when you're building something, when you, especially if you have a complex prompts. So here, that just talks about the same thing. Now, token limits and rate limits on the next thing we can quickly go over. Okay. So context token limits. So models, all models, they have a certain limits of the context window. Context window basically means the input, the system prompt that you provide, plus the data that you provide after, right? So like, what does that mean? Let's say you want, you have this medical document, which is pretty complex, and you want an LLM to go over it, extract certain information, and return it as JSON-L for you. So you have a really large prompt. Let's say your prompt is something like this, like a 400, 500 lines of basic prompt. And you basically need to send this plus that to your model and wait your model to basically generate the output. So you need to, as part of tokenization, understand this, how many tokens is here, plus how many tokens is here. Plus, there are some of the models, they have some additional, they have their own system message. That will go in the model, and the model will have a fixed context length. Most of the time, it's like a 32K. But you will see like on Gemma models, Llama models, they are saying experimental 128K context window, but that's also experimental. Remember, the original is about 32K. Experimental, you can go up to that point. But I highly recommend you try to get sense of for your product, whatever you're building, get sense of the tokens, the prompts that you have, and the cost it will have, and also how much it can generate, depending on the model that you're using.
Just a question. So the models which has been generated by trained by Big Tech has been trained on multiple languages, right? So is it possible that, let's say if I type something in English, the first step I do is translate it into some language which takes less tokens, like maybe Mandarin, and then pass it?
No, so in order for a model to read this and translate, you need to read entire.
No, I mean, I put the extra layer on top of before passing it to the API.
So who does that translation?
Some other open source model which has been deployed.
So you're basically, I see. So what he's saying is that before I call to the expensive model that you have, I have an open source, maybe a local model that does a really good job at translation.
Yep.
I pass from English, maybe to Chinese. I don't know if it's like this number of characters, but you build the translation of that, and then you pass that to the model that you have, which is multi-language model. Probably possible. There are a couple of complexities here. One of them, it could be simply the cascading effect. how do you know that translation did not ruin the meaning of whatever document you are basically putting? If it's a really sensitive document, you could easily make a mistake. If it's not a sensitive document, it's kind of like a summary of the news or something, maybe you can do that. But that means you need to ensure that first you're dealing with two models. Instead of managing one, you need to manage two. But you also need to ensure that that model works great. The other thing is that the time, because now your process probably becomes slower. Just a guess, I don't know, maybe because you're shrinking the document, maybe it becomes
Yeah, that makes sense.
larger. But then you taking it to another language, you go ask the model in that language, then it gives you an answer in that language. You need to translate it back. Right?
Yeah.
So it's kind of like, I feel like you will go through more steps to save cost, but probably dealing with lots of breaking systems, so lots of things to manage this program. Right? Not that it's not possible, but probably it has its own pros and cons. All right. Just when you're dealing with the token limits, do some sort of like a chunking, truncation, or dynamic planning. You normally need to figure out this one yourself when you deal with different models. You get some sense of what's the problem that you have. I personally, I think today or yesterday, was working with one of the GEMO models, and it always was returning the final output incomplete. So it was hitting, despite the fact that it has 128 context of like not the real context, kind of like a theory context size, but it was always breaking the answers after 34,000, something like that. So I needed to basically, I couldn't change the prompt, I needed to just change the model. But you need to figure out that one to ensure that you have a complete response all the time. The other one is that API rate limit. Providers always also have some sort of like a request per minute and token per minute limit, depending on which company you're working with. If you pass that, you get some sort of like a 429 errors. I think some companies, they have a better policies. I'm not sure if they have changed it or not. For example, if you work with Gemini, they have limited API calls, not just for you, for everyone in that region. It's kind of like a regional limit. But I think OpenAI is much easier or much faster. All right. If you're dealing with rate limit in practice, if that means that if you have a pipeline that needs to make some API calls, but all of a sudden you keep getting blocked by the API because you hit the wall. So you need to add some sort of like a backup policy. One of them could be like such a like exponential backup. That means that if you hit and you get an some sort of like a 429 error, instead of just making another call, you just wait, and if it repeats, exponentially increase the wait time until to the point that you can basically get the answer back. All right. Just talking about OpenAI with this, we don't need that. All right, last one. We're going to talk about prompt templates and prompt engineering. Not much, but in general. The idea of the prompt templates is that to predefine prompt patterns with certain placeholders for certain models. Not all models have prompt templates, but the one that they have, it's highly recommended to use that, adhere to what they are basically they are giving you. On Hugging Face, you can access all of this. You can also include some sort of like a role or persona to follow instructions. This is just an example of prompt template. You can work with didn't, just an also library from text wrap. So basically you wrap the text that you have in certain specific template, and then you pass it to the model. So instead of you just converting the text, you have a plain text, you wrap it into some template, and you pass the template to your model. You could work with the LangChain version of it, which I'm sure most of you have, seems like everyone here is Langchainer. But and the other one is looking for prompt types and strategies. Why not me to go over this because you probably know better than me. But there are just different strategies that you can use: zero shot, few shot, chain of thought, rule prompting, instruction, and so on. Way more than this. So the idea here, the general idea behind this types of prompting is that you will have one model, one AI model. How could you give basically maybe a couple of examples, or you would put it in a certain role scenarios and ask it to answer, provide you answer in the way that you want. So that's the summary of the idea. Like for example, in few shot, just provide a couple of examples and the model will learn to follow you. If you're basically doing some sort of like it's kind of like a role playing. So if you're saying that you apply it knowledge-based tutor and then you give it an example how it solved the problem, and then you expect it to follow that rules. On the other end, you could also work with chat models, which basically like OpenAI, Anthropic, and Gemini, which basically have certain system structure, user assistant rules. These types of model basically, this is like an example for OpenAI. They receive the prompt in the following form. There's a rule, definition of rule. This is for the system. There's a definition of a user. This is what the user provides. It's going to be different across different models. For example, if you go to Llama 2, the format is different technically. If you go to I thought I have Llama 3, but so in Llama 2, basically the format is in this format, and then again, just read the documentation for whatever model you are using. You can find all of this. Almost there. All right, so this is it's just a provider and compliances to just ensure that whichever model that you're using, if you're dealing with the sensitive data, you can't just send it to any random API provider. Either deploy your own model like a local deployment, or if you're deploying to, or if you're working with APIs, be sure that your company has some sort of like a contract, or between the company and maybe, for example, OpenAI, that the data that you're sending is not being used or retained for model training perspective. Just be sure that you follow all of those. All right. Okay, we're going to stop here. We're going to take a break. Then we have a bunch of labs that we want to go over. Have you all have your GCP credential? You see GCP, right? Okay, so we have some labs on GCP. Not that you need to do it in the class, but just to be sure, because I think those credits they expired if you didn't redeem those. All right. Let's take a break. My pleasure. Yeah. Doesn't bring it up, but that's that one. This is not the best time. Yeah, sorry, because.
So you want to do the target expectation, so a project is going to be you should start running locally, or start running on cloud, so you want to know what's
I mean, that doesn't matter to us which one we use. If you can deploy it yourself, I highly recommend you to do that. Why? Because you learn. That's the whole idea of this, right? To learn practical things. API calling is API calling, right? If you can do that, if it's like a smaller model, that's something that can fit in one GPU, so it's definitely. But it's not going to be, if you use the API, that doesn't mean that you're going to.
And what are the expectations of
Depends on what you're going to do. If you can try to, that means you need to have a data. You need to find you need to show the validation result, like a bias check. How do you ensure that after training the model did not forget the original knowledge? Maybe that's the case, maybe you wanted to forget the original knowledge. So you need to basically clarify all those stuff.
It's not a.
Fine tuning.
Because we've tried to get it called. We're trying to vision model for that. We do have some data, but it's quite limited. So there is unstructured data and we will convert it to structure. So we do not have a lot of data for it. So what do you?
Document extraction, like a vision. Type of model.
Yeah, we'll try to convert unstructured data for documents. Structured data.
So. There are a bunch of tool out there. Duckling is one, Quinn. There's one. What you want to do is